we think it's not going to be useful. And is the little camera? Yes, it's going to focus very slowly. Is it? I hope so. Yeah, it looks like it focused. Okay. So we're recording here. We start this. And, right, okay. Lots of stuff to do today. If you record with the view changed, how do I change the, so I go to speaker. At the moment, I don't see myself as speaker. I see somebody else. I see somebody else's name written. View, speaker view, that's what I've got. Top right, yes, but speaker view, it's on speaker view. Everybody sees me, but anyway, we have the little camera, fortunately. So let's just power through this. This is not one of the complicated, this is just to sort of pound in this, before we take any steps, our empty subsolution can be extended to an optimal solution. Suppose that after I steps, blah, 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 blah. This is just going to drive that into your heads, okay? So, interval scheduling, this is sort of one of the classic introductory problems for greedy algorithms. You have some things, some activities. Maybe this is called activity scheduling in the book. Sometimes this kind of thing is called job scheduling, but job scheduling is a whole field. I'm just going to close the browser so it doesn't make beeping noises when people email me or something. Okay, so job scheduling is a whole field because normally, and lots of versions of job scheduling are really hard because normally you have an interval, you have a start, a release time, and you have a deadline, and you can move the job around, and maybe you have multiple machines and blah, blah, blah. We don't worry about that. We just have some activities. They have start times, they have end times, and they all have equal profit, okay? So these are your activities. You can see these, right? Yes? Yep. Okay, so you have, each activity has a start time and an end time, and it has some profit, well, it has, let's say it has profit 1. Okay, so everything is equally important to you. So this is going to be your day. You're planning your day, and you have a bunch of activities you want to do. And they can take different lengths of time, but you value them all equally, okay? And you can't get the profit for one unless you do everything, unless you do all of it. So if you decide to do this activity, it only counts if you do the whole activity. You start here and you do it there. And we imagine that you can't do more than one activity at a time. So you can't like eat lunch and watch the algorithms lecture at the same time. Obviously, in fact, you can, some of you probably are, but maybe you cannot meet a friend and watch the algorithms lecture at the same time, because if you're paying attention to the algorithms lecture, then your friend is going to be annoyed, and if you're talking to your friend, then you're actually not you're wasting the time watching the algorithms lecture. Fortunately, it's recorded, so you can do it later. So algorithms doesn't really fit into this, because you can watch algorithms whenever. So we want to select a subset of these activities. Okay, I'm not going to do that for all of them. And we want to select a subset. We want it to be as large as possible. We want to do as many activities as we can because we value them all equally. And so you're looking, why is Zoom is orange. Okay, now it's not orange anymore. And this is recording, right? Yeah. Okay, so how are we going to do this? So we can imagine these activities, we get them as a set or people are waiting to be let in. Admit all. Wow, there were a load of people waiting to be let in. I'm sorry about that. Okay, please mute yourselves. Sorry about this. It's, oh, yeah, okay. Please, if anybody sees there's somebody waiting to be let in, just like unmute yourself and let me know. Otherwise, please mute yourselves. Or I can just mute you. And I'll just mute you too. Okay. Is there somebody else? Okay, no. So, how are we going to do this? So we imagine these as pairs, maybe, so this is time, and this direction doesn't mean anything. And so, for example, maybe this starts at, let's say, 6 a.m. and ends at 8 a.m. And this starts at 7 a.m. and ends at 9 a.m. And this starts at 8:30 and ends at 9, and so on and so on. Okay, so you're going to get this as a list of pairs. So it goes from 6 to 8 and 7 to 9, and they all have equal profit. And we want to take a scheduling element. Yeah, so these are intervals. Actually, okay, technically I shouldn't write it like that. Technically I should write it like, let's imagine that these are half open, right? So that they're closed when they begin. It starts at 6, but then if it ends at 8, then you can start something else that starts exactly at 8. Okay, so you're super fast. You can get from one class to another, or from one activity to another in 0 time. This is the joy of being in a lockdown. Everything's online, so you don't actually have to run between buildings. You just like switch your Zoom meeting. Okay, how are we going to do this? So I said in the last class that usually with greedy algorithms you sort on something. What we want to sort on. Has anybody seen these before these? Has anybody seen this? You have seen this problem before. Yeah. Okay. Have you seen the proof of correctness? I think, okay, not yet. Well, not from me. But okay, so you sort on the finish time. You might think, ooh, what's the most urgent thing? What's the thing that's going to start first that I have to get ready for right now? But you don't do that. Where is my eraser? You sort by finish time. So let's say instead of 9, that just goes from 8 to 8:50, 8:30 to 8:50. So what we would do, you would look at this. We say, oh, of these, what finishes earliest? It's going to be this one. So we're going to take this one. And then what finishes, well, actually, we could make this 9 o'clock because we would then look at, say, what finishes next? Well, it would be this one. Well, let's say this finishes at 9:10 to make this more interesting. 9:10. Let's say it finishes at 9:10. Well, we look at the one that finishes next. It's this one, but it overlaps this one. So we can't take both, and we've already taken this one. In greedy algorithms, we don't change our mind. So we take this one. We do not take this one. And then we look and we say, okay, this one, does it conflict? No, it doesn't. We look at the one that starts next, ends next. It's this, it doesn't conflict. We take it. The one that ends next is this one, but it conflicts with stuff we already got, so we don't take it. What ends next? It's this one. Let's make this one start here. So that if we'd been considering it by start time, we'd have looked at this one next and taken it, and we couldn't have taken this one. But we're doing it by finish time, so we take this one, and not this one, and not this one, and we do take this one, And so we can't, and then looks like we can take this one. We cannot take this one. It looks like we can take this one. And then we cannot take this one, and we cannot take this one. Okay? So, everybody sees what the algorithm is? Sort by finish time, and then process them in order of finish time, and take it if you can, if it doesn't conflict with something you've already taken. You can't take certain ones again. Oh, because you can't take this one because you've told, you've signed up, you're going to the gym between 6 and 8 because you're much more energetic than I am. So you've signed up for the gym between 6 and 8, you're going to the gym, so you cannot watch early morning cartoons or something, right? Between 7 and 9. So gym, no, so you've taken the gym, so you can't watch the cartoons. But then you can have breakfast. But then you cannot do whatever you do, like between 8:30 and 11. I don't know. Then, so you took this one, so you couldn't take. You took this one, so you couldn't take these two, and you took this one, so you couldn't take this one, because you can only be doing one thing at once. You're maximizing the number of activities. Yes. Sorry if you were one of the people who came in afterwards and I didn't let you in on time. Blame Zoom for lying to me, and then blame Microsoft for producing such a crappy product that I have to use Zoom instead of Teams. Okay, so we understand the problem. We're maximizing the number of activities that we consider them all equal. And to do that, we sort by finish time and we process them and we take them if we can, if they don't conflict with something we've already taken. Why does this give us an optimal schedule? Well, before we've taken any steps, our empty sub-solution can be extended to an optimal solution. So we're processing it in order of finish time. And before we've processed anything, of the stuff we haven't considered, we can definitely take an optimal solution, right? Isn't this? No, this is easier than dynamic programming. I think you probably could. There are versions of job scheduling that you can solve through dynamic programming that you probably can't solve through greedy. But this version is sort of the typical thing for greedy. I think it's in Common Lysis and Reisenstein. Okay. So, before we do anything, we haven't messed up. Now, suppose that after I steps, we've taken, so we're, okay, ignoring this stuff. So imagine we haven't processed these. Oops, I erased one of the activities. Where was the activity I erased? Up there, right? Okay, so we're here. After I steps, yeah, let's say that I steps. So now we've processed up to here, and we haven't looked at the rest of them yet. So after I steps, assume that our sub-solution, the stuff in red, yes, 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 no, no, can be extended to an optimal solution. So that's true before we've taken any steps. Now, we have to show that after we take I plus one step, so we take this one. So at this point, our solution can be extended to an optimal solution. And we're going to take this one. And we want to say, okay, if S does what we do, great, then our sub-solution after I plus one steps can be extended to an optimal solution, same S. Well, what if S does something different? What if S takes, oh wait, yeah, this one conflicts, so we couldn't take this one, so let's just mark that off, because we want to consider the green one, okay. So what if S takes this blue one? And we take the green one. Okay? So, so before, at this point, our subsolution could be extended to S, but now it can't because we take this and S takes that. Okay? Now we do this exchange argument. We say, well, whatever S did after that, right? So it takes the blue, we take the green, and then we consider what the rest of S. It couldn't take anything else in here because it conflicts with what it's taking. So we're going to call this the rest of S. Okay? So what if we take the rest of S and we say, now we're going to take S and we're just going to switch it. Instead of taking the blue, we take the green. Is that still compatible with the rest of S? Yes, it is. Because if the rest of S didn't conflict with this blue stuff, then it doesn't conflict with the green green activity either, because the green activity ends earlier. So we can take sort of our stuff so far. So what we've done in I steps, and then S takes the blue one, and then it takes the rest of S. So it takes this, what we've done in I steps, it agrees with that. It takes the blue one, it takes the rest of S. We're going to take what we've done in I steps, and then we're going to take the green one, and then we're going to take the rest of S, and we're going to call that S prime. So this is going to be this activity plus the rest of S equals, well, okay, and also what we've done, so what we've done earlier, plus the green one plus the rest of S is, we're going to call this S prime. So S prime gets at least as many activities as S does, because it's the same as S on the red stuff. It differs only on the blue and the green, but this is worth 1, this is worth 1, so fine. And the rest of S, it gets the rest of S, because the rest of S can't conflict on the green. Okay, so we just swap the blue for the green, and we get S prime. S prime gets at least as much stuff, and we're going to admit the person who's waiting. Yeah, sorry about having to stop and admit people. Okay, so sorry about, it's not a webinar, you can't just join. And I will check to see what the clock says. 6 minutes. So, okay, so after I steps we haven't messed up, then after I plus 1 steps we haven't messed up, so by induction we don't mess up, so the greedy algorithm sorting by finish time produces an optimal solution. So long as blue terminates after green. Yes, because we are if blue terminated before green, then we would have processed the blue first and we would have taken it. So it's important that we're processing in order by finish time. Okay, good. So that's first thing we see with after, before we take any steps, our empty subsolution can be extended to an optimal solution. Suppose that after I steps, our subsolution could be extended to an optimal solution S. Then you do this exchange argument stuff, which you actually have to pay attention to what the problem is. And then you say, okay, and so after Then after I plus 1 steps, our subsolution can be extended to an optimal solution S prime. Therefore, by induction, the algorithm produces an optimal solution. Okay. So that's I think it's maybe not its interval scheduling, maybe it's activity scheduling. I forget. It's in CLRS. And it will someday be in the course notes when I get caught up. Okay. So the next thing, suppose we have some sequence of numbers 7, 2, 4, 3, 8, 1, 2, 6, 9, 5, 8, 7, 4, 3. Okay. So we have some sequence of numbers, and we want to divide this. We want to partition it into the minimum number of, let's just say it's increasing. Okay, let's just, so I don't have to keep remembering to say non-decreasing. Can we partition this into the minimum number of increasing subsequences? So increasing means you can't have 7, 2, you can have 7, 9, right? So how are we going to do this? Well, you can sort of, well, I'm actually going to tell you this to save time because we have a load of stuff to get through. So what you do, you start, these are also called chains. So the increasing subsequences are called chains. So you start with 7. Okay, so 7 is the beginning of a chain. And then you look at 2 and you say, oh, well, I can't attach 2 to the same chain as 7 because then it's not increasing. So 2 is gonna have to be its own chain. And then 4. And you think, okay, well, I could either start a chain with 4 or I could attach it to 2. So I could start it or I could attach it to 2. And then you have 3 and you think, oh, well, if I'd started a chain with 4, I could have attached 3 to 2. But now I can't attach 3 to 2. And so I'm going to have to start a new chain. Why do I put it below 2? Because I'm ignoring the 2 now because I can't attach anything else to the 2. I can only attach it to the 4. So now I have a 1. I can't attach that to anything. So I start there. Now I have a 2. I can attach the 2 to the 1 or I can start its own chain. So I'm going to do that. Now I have a 6. I could attach 6 to the 2 or to the 3 or to the 4. Or I could start its own chain. What do people want to do? 4. Okay. 9. What do people want to do? 7. Okay. Has somebody seen this before? Okay. 5. 7, 3. Okay, 3. Okay, 5, 3. 8. 8. Somebody says new. 8 says 6. 6. Okay, 6. Yes. 7. Okay. 7, 4. You always have to put it on the closest number if there are multiple options. Yes. So okay, it's not the closest. It's the predecessor, right? Because it has to be non-increasing. So if I had a 4 and there were a 4 here, I couldn't. If I wanted increasing subsequences, I couldn't put a 4 after a 4. What I do is I put it after the largest number, which is smaller. This is like, I don't know the Windows poker game. Okay, so we're just going to do that. We're going to say 4. And then the 3, I can't do anything. I have to start a new chain. So predecessor, yeah. Predecessor and not equal, strict predecessor. And if there isn't a strict predecessor, you start a new chain. Okay, so this is saying that we have What's the smallest number? Well, we have 7 and 9 are a sequence, and 2, 4, 6, 8 are a sequence. That's kind of cool. 2, 4, 6, and 8. And I didn't actually keep track of which 2s and 4s, but I guess it's these. And then 3, 5, 7. Okay. 3, 5, 7. 3, 5, 7. And now I've run out of colors. So it's going to have to be a red circle for 1, 2, and 4. And 4. And then it's going to be a green square for 3. Okay, so we have 1, 2, 3, 4, 5 increasing subsequences. I have to start the little camera.